All right, good morning, everybody. Today we're going to start talking about concavity, which is topic 5.6 in our AP sequence. And I just want to go over a couple of our first important statements about concavity. And if you remember what we mean by concavity, we are just generally talking about whether a function is concave up, and I'll just sketch a little thing here, what I mean by concave up. There's concave up, all right? And I think you all know what concave down means, all right? Concave down would be the other way, like that, all right? So when we're talking about concavity, the graph of a function is concave up when its derivative is increasing, when the derivative is increasing. Not when the original function is increasing, when the derivative is increasing. It's concave down when its derivative is decreasing. Again, when the derivative is decreasing. All right? So we can also use the second derivative to help us with this. So basically, the graph of a function is concave up when its second derivative is positive. That makes sense to us from the first statement, because the second derivative, of course, is the derivative of the first derivative. So if it is positive, then it is increasing. Then the first derivative has to be increasing. If the value of the second derivative is negative, then it makes sense that the derivative is decreasing. So that's kind of that relationship between the first and second derivative when it comes to concavity. Let's take a look at this problem here from the 2015 AB test. The figure above shows the graph of f prime, the derivative of a twice differentiable function, that's important, on the interval -3 to 4. The graph of f prime has, so they are telling us it's a fact, horizontal tangents at x equals -1, x equals 1, and x equals 3. So we are told there are horizontal tangents here, here, and there. On what open intervals contained in -3 to 4 is the graph of f both concave down and decreasing? Give a reason for your answer. All right? So now we're going to kind of jump right in, put to use what we just talked about. And we said, let's go back to our first slide. We said that it is concave down when the second derivative is negative. So, we're looking here at the graph of f prime. I think we can see that in here, all right, it is decreasing, right? So, we've got a decreasing area here, okay, because our slopes of the tangent line to the derivative would be negative. We've got a decreasing area here, all right, because the slopes of the tangent line there would be negative, all right. So from -3 to -1, when x is between -3 and -1, we can say it's concave down. Okay. And from 1 to 3. Oops, typo. And from 1 to 3, we're concave down. Okay. So that gets us started on this idea of concavity. But what about this idea of where it is decreasing? Concave down and decreasing. So when we talk about this idea of the original function decreasing, we are interested in when is f prime negative. Because if the function is decreasing, its slopes of the tangent line have to have a negative value. Well, that only happens from here to here. So we need to change this first one. If we're going to do concave down and decreasing, we need to change this first one to -2 to -1. The other one is okay because all of these values in here are all negative. So this one is okay already. All right? Let's take a look at this as kind of an example problem. This is a good kind of general, how do we get rolling with looking for concavity type problem. If h of x equals x cubed minus 6x squared minus 7, what are all values of x where the graph of y equals h of x is concave down? Justify your answer. So the first thing we should do here is find the derivative. F prime of x is, of course, 3x squared minus 12x. All right, that makes sense. But we're wanting to know where is this, where is f prime of x decreasing? All right, so if you think about what this function looks like, this is a parabola that has zeros at 0 and 4. You can find that out algebraically, like this. So what I'm going to try to do here is walk you through, several ways that we can tackle this problem. This one, the derivative is a nice, easy function that we know a lot about. Okay, and so we're looking for where is f prime of x decreasing. So we're looking for where are these slopes of the tangent line, where are the slopes of the tangent line to the derivative negative. Okay, and so what we should do is, let's go ahead and find the second derivative. The second derivative is 6x minus 12. All right? And if we set this thing equal to 0 and solve it, we have 6x equals 12. We have x equals 2. That's the place where the second derivative is equal to 0, and that has a special name that we're going to talk about in a minute. It's called a point of inflection. It's a place where the concavity changes. All right? This is where concavity changes. Right here at 2. And we're talking about the concavity of the original function. We're not talking about the concavity of the derivative. We're talking about the original function. The concavity changes there. All right? So, back to our original statement. Where is f prime of x decreasing? It's decreasing from negative infinity to 2. And that's where it is concave down. So we're not just interested in, we have to look at the graph, yes. I could have also checked a function value, right, in the second derivative, right? Couldn't I have done this? What is f double prime of 1, let's say? If I plug 1 into the second derivative, I get -6. So that confirms my point that the function, that the derivative was decreasing there. All right, so we kind of looked at this one a little bit algebraically, we looked at it numerically, we looked at it graphically. And if you were to jump over to the graphing calculator and look at the original function, you would see that this makes sense. If I plug in that function, x cubed minus 6x, minus 6x squared minus 7. And we look at this graph, it's going to make sense. Change my window here a little bit. Let's go change my y minimum to -20. You can see that the function is concave down from -infinity until about 2. All right? If I go down, let's go down to maybe -50. From -infinity, for all of these x values, from -infinity up until we get to 2, this thing is upside down. It's concave down. When we get to 2, this is called a point of inflection, where it changes from being concave down to being, now it's concave up. All right? So let's keep moving forward here. Change with our concavity. All right? Points of inflection. Okay, and this is in your notes, but I just want to highlight some things. A point of inflection occurs where the graph of a function changes from concave up to concave down. Justifications involve asserting either that the first derivative changes from increasing to decreasing, or vice versa, or the second derivative changes signs. What are we talking about here? We're talking about justifications. Okay? In AP Calculus, we have to be able to justify things. All right? And so the first derivative could also have an extremum. To find points of inflection, okay, set the second derivative equal to 0. All right? That is our kind of go-to. So let's take a look at this next problem. Where does the graph of this kind of ugly function have a point of inflection? Give a reason for your answer. All right? So the first derivative, f prime of x, is going to be 1/3 times x minus 2 to the -2/3. We wouldn't need to use the chain rule, but the derivative of the inside is just 1. The second derivative will be -2/9 times x minus 2 to the -5/3. If we set this thing equal to 0 to look for a point of inflection, over here I would have a -2 on top. I'd have this 9 times the cube root of x minus 2, that whole thing to the 5th power. And if I try to solve this algebraically. All right, if I try to solve this, I would multiply both sides by this denominator, and I'd wind up with 0 equals -2. All right, and we might think that there's no point of inflection. All right, but when x is less than 2, the second derivative is positive. And when x is greater than 2, the second derivative is negative. So x equals 2 is a point of inflection. How could we figure that out? Well, try a couple values. All right? How did I kind of get a clue here? Well, if I put a 2 in right here, I get something that's undefined. Okay? That leads to something that is undefined. So that's a clue that maybe I should check things to the left and the right of that in the second derivative. Remember, we're not just interested in where the second derivative is equal to 0. We might also be interested in where it's undefined. And then if you were to check values to the left and right of this, okay, like if I put in a 1 right here, if I put a 1 into this thing, 1 minus 2 is -1. The cube root of -1 is -1. -1 to the 5th is -1. And 9 times -1 is -9. So this thing is positive. Okay? So when x is less than 2, this is positive. So this thing did change here at this value of 2, so it was a point of inflection. Now, a couple common misconceptions. The second derivative, this is what we just dealt with. The second derivative need not be 0 in order to change signs. All right, here's a graph of that one we just did. This is what we know is a vertical tangent. All right? But it is a point of inflection. The concavity is changing. All right? The concavity is changing. This is concave down. This is concave up. All right? The concavity is changing at that value of 2. And I showed you how to come up with that. All right? Another common misconception. Just because the second derivative is 0, that does not mean it must change signs. Okay? We have, we start off with this function, okay? We take its derivative, we take its second derivative. If I set this equal to 0, I get 0. But notice something. There's no change in sign. Okay, this is concave up everywhere. This is concave up everywhere. All right, so you do have to go back and consider what's going on with the function from all aspects, and that will help you in dealing with concavity. And we will stop